Welcome to Periodic Trends in Atomic Properties. So, there are some trends in certain properties as we move across a period or down a group of elements, and these trends tend to repeat for each period, so they're repeating periodically. This is why we call it the periodic table, and this is part of the reason why the periodic table is arranged the way it is. So say every so often we get to some element that is a gas and it doesn't react with much of anything, so we call it the noble gases, or we call that group the noble gases. So we've arranged the periodic table in such a way that the properties of these elements are repeating within a vertical column within a group. So one of the other sorts of properties that we want to look at is called ionization energy. So this is the energy that's required to remove an electron from an atom or an ion that's in the gas state. So we have some atom, symbolized X there. It's in the gas state. If we add some energy to it, we can get an electron to come out of our atom, and we're left with a positively charged ion. Now, we could start out with a negatively charged ion and end up with a less negatively charged ion over here. Or start off with a positively charged ion or whatever. So the ionization energy is the energy required to remove this electron from the species that we start with, the atom or ion that we started out with. Now, the first ionization energy is different from the second ionization energy and third and so on. So the first ionization energy is the energy required to remove the first electron from a neutral atom. So we start out with a neutral atom, we have to put in some energy to get out one electron. And now we have a charge of +1. When we want to remove a second electron, well, now we're removing an electron not from an uncharged atom, but now we're removing it from that ion with a +1 charge. So now we have to put in more energy because it's going to be harder to remove this negative charge from that positive charge over there. And we'll end up with a charge of 2+. So the second ionization energy is always going to be larger, it's always going to be significantly larger than the first ionization energy, because it's always going to be harder to remove an electron from a positively charged ion than it is an uncharged, a neutrally charged atom. So the second ionization energy is always going to be larger than the first ionization energy. So, but also, as we move from left to right across a period, the ionization energy increases, and as we move down a group, the ionization energy decreases. So, we see here as we move from hydrogen to helium, the ionization energy jumps up, and then it goes way back down when we get back to the left side of the periodic table at lithium. And as we go to the right on the periodic table from lithium over to neon, the ionization energy increases. There are a couple of inconsistencies in there, and then it jumps back down. And so when we have the noble gases, so helium, neon, argon, krypton, xenon, and radon, we're going down as we move across the group, and likewise for the alkali metals, especially if you include hydrogen here, it's also in group 1, although it's not an alkali metal. So hydrogen, lithium, sodium, potassium, rubidium, cesium, francium would be the next element listed there. Those are all going down as well. So it's getting easier to remove an electron. It's significantly easier to remove an electron from lithium than it is hydrogen. This is why it's a metal and hydrogen is not. It's easier to remove an electron from sodium than it is from lithium. It's easier to remove an electron from potassium than it is from sodium, rubidium from potassium, cesium from rubidium, francium from cesium, and so on. And so, but on the other hand, it's really, really hard to remove an electron from helium. Not quite as hard to remove an electron from neon, not quite as hard from argon, but still harder than just about anything else. Removing an electron from just about anything else. So, again, that trend is generally seen. Again, there are some variations in here as we move across the periodic table. So the next property we want to talk about is electron affinity, which is kind of the opposite of the ionization energy. So the electron affinity is the energy change associated with the addition of an electron to a gaseous atom. So ionization energy was the removal of an electron from an atom. Well, electron affinity is the addition of an electron. Now, note here that it's still to a gaseous atom, which is uncharged. So we have an uncharged atom, and we add an electron. How much energy we get out as that electron sort of falls in towards the nucleus of the atom. Now, the electron affinity of a positively charged ion with a charge of +1 going to neutral, that energy would be exactly the opposite of the ionization energy, the first ionization energy. So this is a similar sort of idea to the opposite of ionization energy, only in both cases we're starting out with a neutrally charged atom. Ionization energy is removing an electron. Electron affinity is the addition of an electron. So what we're measuring here is essentially how much the electron is, or the atom is pulling on electrons that are outside of it. And we're measuring that in terms of the energy that's given off here. So the trends in electron affinity are electron affinity increases as we move from left to right across a period, and the electron affinity decreases as we move down a group. So now let's look at atomic radius. So what we mean by atomic radius is the radius of a single atom. It's usually defined as half the distance between two nuclei in a diatomic molecule. So if we have two atoms of the same element bonded together, we've got the nuclei at the center of each atom there. Well, that bond length from the center of one nucleus to the center of the other nucleus, if we take half of that, then that's what we're defining as the radius of the atom. It's a little nebulous because the electrons are forming sort of a fuzzy cloud in there, so we don't really have, you know, a nice spherical structure like I've got drawn here. So the atomic radius decreases as we move from left to right across a period, and they increase as we move down a group. So you can see that shown here as we move from hydrogen to helium. We're decreasing from a radius of 53 picometers down to 31. As we move down group 1, we go from 53 to 167, 190, 243, 265, 298, so on. So, but in general, as we move to the right, the atomic radius is getting smaller. As we move down the group, the radius is getting larger. Now let's look at electronegativity. So electronegativity is the ability of an atom to attract electrons. So again, this is somewhat similar to the electron affinity, but it's not measured in energy like electron affinity was. This is a different sort of quantity, and so this is, again, similar to electron affinity, but electron affinity was the energy given off when the electron is added, whereas electronegativity here is a measure of the attraction. So this is a measure of the force there. The attraction of the nucleus for the electron outside the atom. So the electronegativity increases as we move from the left to the right on the periodic table, as we move across a period, and it decreases as we move down a group. So what that means is that at the top of any group, we have the most electronegative element within that group. So hydrogen is significantly more electronegative than lithium is, and the electronegativity decreases from there. As we move from hydrogen to helium, note here that the electronegativity for the noble gases is listed here as 0 because essentially they're happy the way they are. They don't want to gain electrons, so there's not really much of a pull for electrons outside of them. They don't really have electronegativities of 0, but it's too difficult to measure them, so we generally list them as 0. On a lot of charts like this, they're just not drawn at all. So note that as we move to the right on the periodic table, the electronegativity is getting larger. So the halogens here, within a period, the halogen will always have the highest electronegativity, and if we move up to the top of the column, we've got fluorine. Fluorine has an electronegativity of 4.0. That is the highest electronegativity out of all of the elements. The lowest out of all of the elements that we found so far, at least, would be francium, which is not even shown here. That's the next period down. So let's see if we can explain why we see these trends that we do, and see if we can tie them all together so you don't have to memorize what's going on, you can explain why the trends are the way they are. So the trends in atomic radius can be explained by the number of protons in the nucleus and the energy level of the valence electrons. So remember, as we move to the right on the periodic table, we're adding protons to the nucleus. Right? As we move down on the periodic table, we're also adding protons. So as we add protons to the nucleus, that means that the attractive force between the nucleus and our electron is increasing. So as we move to the right on the periodic table, that attractive force is increasing. If that attractive force is increasing, then that electron is getting closer to the nucleus. So as we move to the right on the periodic table, the atomic radius should be decreasing, which is what we see. Now, when we move from the right side to the left and down, as we move down on the periodic table, we're adding one more shell. Our valence shell is getting farther out from the nucleus. That should mean that our atom is getting bigger. Our atomic radius should be going up. So as n of the valence shell increases, as that principal quantum number increases, the average electron distance to the nucleus is increasing. So because now we've added another shell outside the one that we already have. So as we move to the right on the periodic table, our atom is getting smaller. It's shrinking because we're adding protons into the nucleus, but the electrons are still in that same energy level, but now they're being pulled in tighter and tighter to the nucleus. So as we move from left to right, the electrons are getting closer in, the atomic radius is decreasing. As we move down, we're putting electrons outside the ones that are already there, and so the atomic radius is increasing. So overall, as we move down, the atomic radius increases. As we move to the right, the atomic radius decreases. Now, given that the atomic radius is decreasing, we should be able to explain the other trends, or based on the way the atomic radius is changing. So, the ionization energy, electron affinity, and electronegativity can be explained by our trends in atomic radius. So as the atomic radius increases, the electrons are getting farther from the nucleus, that attractive force is decreasing, which means that for that electron, for our ionization energy, we're always removing the outermost electron, because that's the electron that's easiest to remove. So as our atom gets bigger, it's going to be easier to remove that electron because it's farther from the nucleus. So as we move down on the periodic table, we're getting larger atomic radii, and that means that we should have a lower ionization energy, which is what we see. As we move down on the periodic table, ionization energy decreases. As we move right on the periodic table, the atomic radius is decreasing. As that radius gets smaller, it gets harder to remove an electron, which means as we move right on the periodic table, the ionization energy should be going up. If you look back, that is in fact what happens. Let's look at electron affinity. As we move right on the periodic table, our atoms are getting smaller, our radii, our atomic radius is getting smaller, and so our electrons are getting closer to the nucleus. An electron that's outside the atom gets closer to the nucleus, is able to get closer to the nucleus, and that means that it is going to experience a greater force pulling it in. So the electron affinity should go up as we move to the right on the periodic table. As we move down on the periodic table, the radius should be getting bigger. An electron that's on the outside has to be farther away, and that means the electron affinity should be dropping as we move down on the periodic table. That's what we see. Now let's look at electronegativity. The electronegativity is again a measure of how strongly the nucleus is pulling on the electrons that are outside the atom. As we move to the right, the atom is getting smaller, but it has more protons in the nucleus, so it should be pulling on electrons more strongly. As we move to the right on the periodic table, the electronegativity increases. As we move down on the periodic table, the atoms are getting larger radii. That means that the electron is farther away. We should be pulling on the electron less. The electronegativity should be dropping. That is in fact what we see. So, down and left, we see very low electronegativities because we have very, very large nuclei, or very, very large atomic radii. As we move up into the right to fluorine, we have very, very small atomic radii, so we should see very, very high electronegativity, very, very high ionization energy, a high electron affinity, which is in fact what we see. So that was periodic trends in atomic properties.